Hello everyone, in this lecture we will be going over Iran Team Selection Test 2011 problem number 1. Here's a view of this problem. We are given an acute triangle ABC where angle B is greater than angle C. Let M be the midpoint of BC, you can clearly see M marked here, and let E and F be the feet of the altitudes from B and C. So E and F, you can also see it here on the picture. Let K and L be the midpoints of ME and MF respectively, and T be on line KL such that TA is parallel to BC. Prove that TA is actually equals to TM. Before I begin solving this problem, I would like to remind you of one of our previous videos where we discuss lemma 1.44 from Evan Chan's 2016 geometry book. Accordingly, it is pretty much the same configuration. We have a parallel line here going through A parallel to BC. E and F are the feet of the altitudes. We did draw the circumcircle of AFE, and it turns out that this line L, EM and FM are tangent to our circumcircle thanks to the fact that KM is the diameter of the 9-point circle. So therefore I'm making use of this lemma here. I assume we already established that, and by this lemma we know, let me write that down, we know that line L, EM and FM are tangents to the circumcircle of FAE. Now let's complete the construction. We are told that the midpoints of ME and MF are K and L. So probably here, let's call this point as K, and maybe midpoint somewhere here. That's the point L. Let's go ahead and join these lines. Let me use a red color here. So when I actually go ahead and join those points, so somewhere here, I guess. So that's the point T, apparently, and we are told to prove that TA is actually equal to TM. So this distance here. So therefore, that's exactly what we want to show. So show that TA is equal to TM. Notice that T is on this line and TA is parallel to BC. Now I want you to focus on these tangent lines EM and FM. Apparently K and L are the midpoints of those two tangents. That reminds me of an earlier result. Let me open a new page and describe this result here. When we are given two circles, namely, let's say we have this circle here and another circle like this, and it turns out, so this is a very well-known result, that the tangents, the external tangents, something like that I should say, when you draw the external tangents like this, there you go. So when you have your external tangents drawn, it turns out the radical axis, so this is O1, this is O2, and we can easily connect those centers of circles, and obviously these three lines, they concur at the same point. You can call it P, I guess. The claim is that the radical axis, so when you draw the radical axis, let me go ahead and draw it with a different color. So let's say this color here. So we know that the radical axis is obviously perpendicular to the segment joining the centers of these two circles. So the question that I have, my concern is the intersection of our radical axis with these two tangent lines. Let me call that point as M, and because M is on the radical axis, so this is the radical axis of omega 1 and omega 2 apparently, I would like to see if there's anything special about that point M. Let's focus on this upper tangent line. The tangency point here is T and here is S. So obviously I can draw perpendiculars here and here. to the tangent. These are 90 degrees, obviously. And let's focus on the left-hand circle first. I can look at this thing here. So if I draw the line which goes through M and O1, and I can try to figure out what is the power of point M with respect to the first circle. So therefore the power of the point M with respect to omega 1 would be simply equal to, if you remember, MO1 plus R, which is R1, I should say probably, so times MO1 minus R1. So let me write that down. So therefore it would be MO1 squared minus R1 squared. But I know very well that that number must be equal to this number here, to the power of point M with respect to the second circle, omega 2, and we just realized that the power of M with respect to that circle would be simply MO2 squared minus R2 squared, and those two numbers are actually equal to each other. Now notice that MO1 squared using Pythagorean theorem in triangle MTO1, and similarly using Pythagorean theorem on triangle MSO2 again. So we know these two are equal. First of all, let's write that down. MO1 squared minus R1 squared is equal to MO2 squared minus R2 squared. Second of all, I will replace R1, I will replace MO1 with O1T, which is simply R1, obviously. R1 squared plus TM squared. So therefore we have, so this expression on the left hand side is simply equal to TM squared plus R1 squared minus R1 squared. Remember that MO1 is just this first expression here. And for the second one, so here this one is SM squared, SM squared plus R2 squared minus R2 squared. But these two expressions must be equal because because of this transitive thing here. So therefore R1 squares cancel out, R2 squares cancel out. We realize TM squared is equal to SM squared, which simply implies TM is equal to SM. So therefore the radical axis will meet the tangent line at its midpoint, and the same thing here, obviously. So that result will be useful in solving our problem at hand. Now going back to the original construction. Now notice that the midpoint L and K, so we are given these points, when we extend the line they meet the point T, and consider the two circles. The first circle being, I call this circle omega 1, the circumcircle of AFE here, and the second circle I have in mind, omega 2, is simply the circle centered at point M with radius 0. So this is a special purpose circle here, and notice that I would like to see where the radical axis of these two circles is. Obviously it will be a line perpendicular to KM. K is the center of omega 1, M is the center of omega 2. It will be a line perpendicular to KM. Moreover, it will hit the radical axis will hit the midpoints of the tangency lines, but the tangency lines are simply EM and FM. So therefore KL is actually the radical axis of these two circles. So let's write that down. KL is radical axis of omega 1 and omega 2, but then it means T is on that radical axis. So therefore T is on that radical axis by definition. Now let's find out what is so if T is on that radical axis, its power with respect to those two circles must be equal. So the power of T with respect to omega 1 is simply TA squared, and that should be equal to the power of T with respect to the circle M, or omega 2 centered at M, but that's simply TM squared. The squares would cancel out, and therefore TA is equal to TM as we wanted to show. So that proves this beautiful problem. Hope to see you in our next video.